formula, it could be a pattern, it could be an algorithm. People call it a recipe, an instruction, or a model. And the official ML term is a model. So it's some sort of mathematical representation of the system. And so now when you go to deployment in traditional software, it's the same thing. You deploy this software and on a server, your user gives it an input, they get an output. And in machine learning deployment, we call it the inference phase or the prediction. Now it looks like software development. So you take this formula that you've gotten in the training, you give it to a computer, your user gives it an input and gets an output. Sounds good? You see, the main difference is that in machine learning, sometimes we don't even know the formula. We don't understand the patterns in the data. And so instead of us figuring them out, we have computer systems figure them out for us. Good? Okay, so how is it different from statistics? Well, to answer that question, let me tell you a little bit about the types of analytics. We talk about 4 different types of analytics. Descriptive explains what happens. So when you are looking at a population or something, you look at the mean, the variance, and all of that stuff that describe a certain population. That's called descriptive analytics. After that, you can look at diagnostics. So you explain what happened. So let's say something happened, there's a lot of rain. You can measure the rain and say, okay, well, we had this much rain falling in the season. The diagnostics says, well, why did this happen? What is it that caused this to occur? Predictive forecasts what might happen. So now that I can understand a little bit of the system and how it works, can I predict the future based on information that I do know? And prescriptive, you recommend actions based on what you know. So now if I can predict something with great accuracy, how do I change my behavior as a company, as a system? How do I change my behavior to be better suited for the future? So these are the little scale of things as we go forward. And so it goes, of course, from hindsight to foresight. As you move through the scale, you're looking more and more towards the future. You're looking more and more towards information you don't have. And statistics really excels at the beginning of the scale, right? Statistics is really interested in looking at descriptive statistics and describing population dynamics, whereas machine learning really excels at the other end of the scale. We're really interested in prediction or in the future. And so statistics and machine learning are both parts of the data tool set. They both aim to define mathematical representations of the real world. But statistics is more concerned with understanding population descriptors, while ML is concerned with predicting unseen data. So the superpower of machine learning is really prediction. So it's using information you do have to fill in information you do not have. And the importance of that is it allows you to reduce uncertainty and to be prepared for the future. And humans really have been obsessed with predictions for a really long time, right? So if you walk on Saint-Hubert Street, you see a lot of they're forecasters in a sense, right? They predict. And if you go way back to the Greeks, people went to oracles to predict things like who wins a war and what happens with this and what happens with that. So all these 3 things, ML, oracles, and fortune tellers, have a different back end, but the point is we're all interested in prediction as humans. Sounds good? Questions? Good? Okay. So I'll take you a little bit through machine learning terminology, just because we hear a lot of buzzwords. People might not know what they exactly mean in the field. So artificial intelligence, or AI, are techniques in general that enable computers to mimic human behavior. So that's anything. It could be a robot that mimics people. It could be machinery that do certain human tasks. So it's a really big field. Machine learning, or ML, are AI techniques that allow computers to learn without explicitly being programmed. And so what they're actually mimicking is the human learning part of the behavior. So artificial intelligence is the bigger circle. ML is a subset of that. Things that are artificial intelligence that are not machine learning are things like robotics, right? Because you explicitly program a robot to do certain things. And things like NLP, syntax, and semantics. So understanding languages through language rules and so on. Deep learning is a subset of machine learning which uses multi-layered neural networks, they call them. They mimic the architecture of neurons in a brain. And so that's one of the algorithms that ML uses. Other algorithms that are not deep learning are, for example, SVMs and XGBoost. And generative AI, which is the biggest type, is a type of AI that allows computers to generate new content. That's the generative part of generative AI. Good. I should say the slides are all shared. They should be at the end. There's a QR code, and you can download all of them. Okay, so ML, where does ML fit in machine learning? When should we use machine learning, and when should we not? Well, I tell my clients that anytime there's data, then machine learning is an option, right? You could use it. ML, though, is a great fit when there's scale, when there's change, and when there's complexity. Scale because machines scale much better than humans. So if you're a company today, you're running an operation, let's say a call center, and tomorrow you get very popular and you want to double your size, well, to do that on a manual system, you have to hire twice as many people, train twice as many people, get twice as many infrastructure and space and so on. Whereas if it is a machine learning system running on an elastic cloud system, you could probably double it within a few clicks of buttons, right? And so scale is a great use case for machine learning. Change, well, because the world we live in today is very connected, and things change very fast. And for us to, think of social media and things like that, for us to just react to change, first we have to understand that there is change, something has happened. Then we have to quantify it, we have to understand it, we have to change the system, and then we have to deploy it. The problem, of course, is that today change happens so fast that to do that loop is really not feasible. And so when we run ML systems with ML ops, we can have listeners to detect change. So we can look at data descriptors and we can detect change and make the system react quite fast. And then there's complexity. So as humans, we look at the 2D, we can visualize 2D systems, 3D systems, maybe 4D systems with time. But when you have multiple dimensions, when you have something that has hundreds and thousands of dimensions, we can't really grasp that. But that's exactly where ML actually shines, is because it really does well with complexity. Okay? So when should we not use machine learning? Well, if there's not enough data, machine learning learns from data. And so one prerequisite is that you have to have data. You have to have enough data, and it has to be of good quality. And so if you do not have good quality data, then maybe you should rethink what you need to do. Maybe collect data before you start. You should not use ML if you have simpler solutions, right? Machine learning tends to be, it's involved. You have to get data, you have to train a model, you have to deploy a model, and so on. And so if statistics works really well or some other system works really well, then maybe machine learning is not the best option. And if it's not cost effective, right? You have to look at what your return on investment is when you put these systems into play. Okay, all good. Okay, so this shows the ML automation stages. People assume, or at least companies that I work with assume that if you do an ML system, then it's 100% automated, and that's really not true. There's always a spectrum of things. So on one end, you have human-only systems, which are systems that are fully run by humans. On the other extreme, you've got machine-only systems. So this is full automation. There's no humans in the loop. But in between, there is a full spectrum. So we've got something called shadow mode. This is where a machine learning system shadows a human, but the human is in control. And we could do this for compliance reasons. We can do this for training reasons. We can do this for all sorts of reasons: monitoring, compliance, training. On the other end, there's AI assistance, which means that the human is still the primary driver, but they can tap into a system that can provide them with information. And we see this a lot, for example, in call centers where you are speaking to a human, but they have an auxiliary system that they can tap into for information. And then there's partial automation, where now the machine is in control, and there's human gating in the background to validate and improve. And so it doesn't have to be full automation, you can choose any one of the spectrum as a company. Good. Good. Let's see. Okay. So the machine learning lifecycle, this is the machine learning process. So this is what I do on a daily basis. And I tell people that machine learning is really based on 5 pillars, right? The business pillar, which because software in general, tech in general serves the business, it serves some sort of purpose. And so you have to always start with that. What is the objective of this system? And that's true for software development as well. And so we first start with what the problem we're solving is, how do we frame it? And framing the problem in machine learning means that this business problem that we're trying to solve, how do we project it into mathematical space? What does it mean? What are the KPIs? What am I trying to get? What is the closest metric that will allow me to be closest to the business problem I'm solving? And so first we frame the problem. We look at the objectives and what ML tasks we want to run. And then we look at the data. So we collect the data, we run data engineering, feature engineering, and then we label it. And then of course we go to the model. So we select a model class, we train the model and we evaluate it. Then when we're happy with it, we deploy it and serve it. So that's where the DevOps loop comes in. Cool. And this is a loop. We keep going until we're happy. And of course, it used to be a few years ago that you did this once, put a model out there for 6 months, and then you were happy. And today that doesn't work, of course, because we live in a very fast-paced world. So model training, this loop is constant, it's endless. It's happening all the time. It's just what the nature of things are. Sounds good? Okay, so machine learning on AWS. Why AWS? Well, one, because it's my favorite cloud, but 2, because it's one of the biggest clouds. It runs things in a way that a lot of other companies as well use. So what I want to show you here is that this is the ecosystem, the ML ecosystem on AWS. And the way AWS thinks of machine learning is very interesting. It wants to serve many different clientele with many different personas. So at the bottom here, this is an old picture. I couldn't find a newer one, but so all of these might have changed. There's more stuff, but the point still remains the same. So at the bottom, there's really low-level infrastructure. So there's hardware, there's really fundamental libraries that you could use. And that somebody like an ML engineer who builds things from scratch would use those, but not everybody needs those. And so on top of that, they have kind of abstracted ML services. They have SageMaker, which is a development environment. And data science people would always tap into this layer. They don't necessarily need all of the stuff in the lower layer. And then on top of that, they have a bunch of pre-trained AI services that you can just tap into, and those are for anybody. And so, for example, if you want to change, if you want to have an image and describe it, then you would go with AWS recognition. If you want to go speech to text, then that's transcribe. If you want to go text to speech, that's poly. And these are already pre-trained. You just call an API. And so the way it works is that there's this layered cake of services, and as you go up, they're easier and easier to use. They're abstracted away for you. But as you go down, there's more control for what you want to do. And this, I think, is a model that all other clouds are also using, the idea of targeting many different personas and having a different set of tools for different people at what level is useful for them. And this is true for the generative AI stack as well. And so you've got your infrastructure at the bottom, you've got your platforms and environments in the middle, and then you've got pre-trained systems at the top. Okay, so this is my last slide, brains versus bots. Any questions so far? No? Yes?
One of the biggest that you're talking about how you have a spectrum of processing automation. Usually, is that where we end up with? Sort of have to add more to the current process?
How, you mean pushing them through the spectrum to the end? It depends, I think, on people and how wary of technology they are. I mean, you've got technologists who think humans are fallible and humans make mistakes, right? And so they would rather automate. And you've got people who like Excel sheets and people sitting on Excel sheets because they have, so I think it's more of a human trust issue and who's in the leadership of your company, right? If you think of, if it, I mean, I love computers because they don't make mistakes. They're assuming a system works well, it does the same exact thing every time. When you come in to clean data, the moment humans touch that data, it's a pain to deal with because one day they put a dot and one day they don't, and one day they put capitals and one day they don't. And you know, machines, they do the same thing all the time. Anyone else? Okay, yes.
I've got a question how I always ask for that work in data science and all that, but more about AGI. How close are we as you are, a professional? What's your intuition? How far in that?
So a lot of people like Elon Musk and people at OpenAI will tell you we're very, very close to AGI, maybe in the next 5 years. And people who know that what they're talking about, or other people, let's say other people, like Dr. Jan LeCun would tell you that it's not even, AGI is, it's general artificial intelligence. It's the idea of creating machines that are as good or better than humans are. And so this machine that will outdo us as humans. And what Dr. Jan LeCun keeps saying is that AGI, in a sense, doesn't exist. Your intelligence is different than mine. There's not a single human today that can do everything. We are very specialized as people. And the doctor doesn't know what a gardener does. And so AGI today as a human level doesn't exist. And so can we eventually build machines that can do a lot of things? Yes, we can, but not in the way the general public is thinking about it. In a sense that if you create a system that has several models that work collectively, you can get somewhere pretty good. But AGI is a concept. Today, we don't know a single human being who is AGI. Like I think it needs a lot more metrics as to what it really is and where do we really want to get to. Yeah. Okay, so human brains, which is my passion. So how do human brains compare to bots? Well, so if both brains and bots are predictive machines, which is, it's great for computers. I just told you their whole point is to predict. I think what came as a surprise was to neuroscientists. We did not think the brain is a predictive machine, right? Because we thought that the brain reacts to sensory information. The reality is that the brain acts before the sensory information hits it. And so when you drink water, you feel better the moment you drink the water, although it's going to take another 15 minutes for that sensory system to sit. But your brain is predicting that the system will be stabilized. When something startles you, you react a lot faster than you can wait to see whether it's worth getting startled over or not. And the reason is because if you think of how our ancestors evolved, a human that waited to understand would have been a human who got eaten and did not pass their genes through. And so the brain, in fact, is a predictive machine. And the way it works is it predicts, and then it gets feedback, and then it corrects, and that's how we work. And that was a surprise, I think, to a lot of neuroscientists a few years ago.
When was it discovered, this view, the fact that the brain is a predictive machine? It's pretty new, no?
I think it's in the last decade or so, and I think the idea, I always thought that we learn about machine learning from the brain, but it's really interesting that we've learned a lot about the brain from machine learning, because when you try to create a system, you start to look at what really exists. And I think it's really after machine learning got really popular that neuroscientists started to ask these questions. And so I think it's been a decade or two, not longer than that.
We already knew, at the people who do sports, certain level, they do, for example, the race before even doing it. So
Yeah.
kind of, they know before they actually do something, what's going to happen.
Yeah, yeah. But I think all of that processes, when we watch them unfold with machine learning and build these models, we ask, well, what is the brain doing? And I think that's been really interesting. So base counts. Well, the brain has about 100 trillion synapses. Synapses are neuron-to-neuron connections, right? And so there's about 100 trillion of them. Those could be thought of as the parameters. Machine learning models are sized in parameters, and today the state of the art is, you could say GPT-4 maybe, and that's about 1.8 trillion. And so the brain is still about 50 times interconnected than our best model today. And it's still much better at integrating data holistically. Machine learning models are they're very task specific at the moment, and they don't take data holistically like the brain does. In terms of training time, while we've been evolving as a species for about 300,000 years, my own has been training for about, you fine tune your own model for the age of your life, so about 3 decades or so. And we have extremely good knowledge sharing. The reason humans evolved to dominate the world is because we teach our children. We have this hierarchical, generational knowledge transfer, right? We teach our kids and they teach our kids. And today there's all sorts of research that's happening across the world, and we can all tap into it collectively. So this collective knowledge use and transfer have really given us an edge as humans. The bots themselves, well, machine learning is, the first few papers came out in 1940s, 1945. And so realistically, it's about 80 years old at this point. But it's a field that is really fueled by a lot of interest and a lot of money. But it also gains from our own brain ingenuity. So it really profits from our knowledge base. And so bots have a lot less time, but they really benefit from who we are and what we know. Speed. Well, the way the brain works is it sends neurotransmitters, so little chemicals that diffuse in liquid, and that's very slow. So it's about estimated at about 200 hertz. On the other hand, the way bots work is they run electrons through transistors, right? You've got electricity running through metal. And today we've got CPUs clocking at about 10 gigahertz, which means that bots are about 50 times faster than the brain can ever be. And that's on the rise, right? Every year we've got better chips. Every year we've got better systems. And so we're not going to win that race. That's not going to happen. And then in terms of input modalities, we get information from our 5 senses, and we're tethered to biology. You can't really get more sensory information in the brain than the 5 senses. Whereas for bots, it's really unlimited. So if you've ever gotten an Arduino and set it up, you know that you can go to AliExpress and buy hundreds and hundreds of different sensory and IoT inputs that you can have this system read from. And so bots have unlimited input streams. And so from there, we're also not winning that race ever. Yes? Yes. I have a lot. So that's an article that I wrote about this topic, and there's much more to it than that. I just told the ones that are obvious. There's a lot of really interesting things, like, for example, the brain, the structure of the brain changes as we grow and as we learn, whereas a machine learning model is very static. Once you build it, it doesn't change itself while it learns. It just changes, it tunes parameters. And so there's a lot of there, not energy consumption though, but
I think like basic situation again, and
yeah.
it really needs to
right? Extremely energy efficient and able to what they would do versus what we're doing with amounts of energy carbon right now.
Yeah, I can add that, but yeah, there's a lot more in that article that I wrote, so you can take a look. But yes, and it depends if you're looking at a brain as a separate entity or you're looking at a human per se, right? Human activity becomes a different ball game in terms of what we've done in terms of climate and stuff, right?
Well, I mean, you're looking at computation and energy consumption as human.
Yeah.
You know, even walking versus taking a car as a human, walk same distance as a car and consume a fraction. I mean, literally a fraction of the amount of energy that it takes to drive a car. Obviously, the car gives you great benefits that it's not measurable. Energy, the energy there, and say
It's
I'll do
important,
that.
especially when you consider a world where you have less energy. What you say is, oh,
well, it's not the availability of energy; it's the cost of consuming the energy in terms of carbon footprint that's going forward.
I'll add that to my list of constantly comparing the two. And so just to finalize the slide, well, machine learning systems have huge potential because of their speed and augmentation capability, which we cannot do. And so they will eventually be the working horse of the future. And so I advise everybody to know what machine learning is and how to use it, because it's not going to go away anytime soon. And that's it. So I've got a ton of resources for anybody who's interested. These are some of the things that I had gone through 10 years ago when I was getting onboarded into the field. And that's it. These are my slides. Yes.
just a comment. Your talk was great.
Thank you.
Really appreciate it. It's incredible. And I just want to mention, especially as you made your study at McGill, you probably know a website called Le Cerveau, Cerveau at McGill. And I just want to mention that the guy who is behind this website, Le Cerveau at McGill, just published a book, a very incredible book, which compile all the recent discovery in neuroscience. So it's Christmas is coming, and it's be a good gift.
Yeah. Okay. I read a book. I read two books that The Intelligence Machine, I think it's called. There's two really good books that do exactly that. They compare human to machine learning.
It's a book only on the brain.
There's that who? Okay. Who's the person who?
Bruno Dubuc.
Okay. I'll look it up. Yes.
In your experience so far with the clients that you're working with, what would you see as the most common human-machine interaction pattern that's that you're implementing?
So we are mostly implementing the one before last, which is the semi-automation, in the sense that you have a system of machine learning that's working, but then there's gated monitoring and approval. So very, very few companies, I think, today have a fully automated system, besides the Googles and the AWSs and the Metas of the world. Most companies have some sort of gating that goes through. But we do see enough people that are comfortable enough with ML automation to make it part of their process.
Do you have any examples that you can share of
So I'm building a system this week that these are companies that do we're seeing a lot of companies do document processing, because as the world becomes more digitized, all of these companies with PDFs and all of these sorts of things have to digitize them. So I'm building a system where a document is scanned and then it goes through AWS TextRact, and TextRact reads it. So it's an image to text processing, and then that information goes through the system, and then if based on how TextRact is confident or not, it goes through a system called A2I, Augmented AI, which allows a human to take a look and say, okay, this was not very confident. Is it true or not true, and so on. And the end process of that all is that now you've got millions and millions of documents that are automatically digitized.
Is that for use with like version or?
No, so retrieval augmented generation is a part of generative AI. I did want to talk about generative AI a little bit here, but the 30 minutes is really not enough. Generative AI is a very different type of ML. It's machine learning that has more to do with more general tasks than specific tasks. And they tend to be very, very large models. I think maybe this would be interesting. Let me go through this. Those are all my backup slides, but okay. So there's predictive, actually, let me go back. The foundations of ML, like I told you, are data, mathematical algorithms, and computer systems. If you looked at a book, a machine learning book about 3 years ago, they would have told you that types of ML are supervised, unsupervised, and reinforcement. And I talked a lot about, everything I talked about is really supervised learning in some sense. But if more recently, November 2020, now there's an added type, which is generative AI, which was unleashed by ChatGPT, right? And so all of the three are now called predictive machine learning, and the last one is generative AI. Now, in terms of the scale of it, predictive ML tends to have models that are a lot smaller, so maximum in the millions. The biggest I have ever trained is 64,000 CNN. Generative AI tends to be in the billion to trillions, and that's where your energy consumption issue comes in, right? In that generative AI is really quite large, so you need these supercomputers to run it. And just to give you an idea of consideration, you've got these models that now go up to 2 trillion, and they keep going bigger. But if we size that, one parameter takes 32-bit float, right? So 4 bytes on a system. So a billion parameters. When a model is a billion parameters, it takes about 4 gigs of RAM for parameters. But to train it, you need 20 times more of that. And so a billion parameter model needs about 80 gigabytes of RAM to train. And this is a billion. We're talking these things are 1.8 trillion GPT. Like imagine that's where all of the consumption come in. And it makes it really hard that most people can't afford to do this.
Do you have an idea of the number of servers required to have this kind of model?
I think I was reading it this morning in a book, and it was like, I think Meta's model was trained on 16,000 NVIDIA GPUs. 16,000, 16000.
Using 800. Yes.
Which one?
Yeah, and you
No, it's the new one. It's the H100.
yeah.
It's the better one.
Okay, yeah.
They
But
took
the one you read about.
16,000. It was the
Okay,
H100, I think.
Okay.
It was the new one. So these clusters are absolutely crazy in size. Yes.
Are we closer to make, traditional AI, so not Gen AI, but predictive machine learning or deep learning? Are we making, winner choices now? Are we there that intent in the
Winner
world of
choice,
machine learning?
meaning
Are we aiming at making it more efficient, that consume less energy, models, or I don't know?
so the idea is that if you want a very specific task, then a smaller machine learning model that is trained on your data is a better choice. If you want to do a very general task like language, you're not going to go in and train it on the world. That's what a Gen AI model is. The problem that's happening today in society is that Gen AI is a buzzword. Everybody wants it. Even though there might be better solutions fitted out there for the particular task they're doing. So I think when the hype goes away, we will be in a place where we're going to say, well, this system is better for that task, and this system is better for that task. Right now, what people are saying is, I want Gen AI everywhere for everything. And that's very frustrating for someone like me. Like, no.
Also possible, like drag systems with smaller models, so you rely more on the context and use a smaller model
Yeah.
that will better
Yeah.
having to rely on.
Yeah. Yeah, and there's a lot of work. I mean, these numbers are not these translate to really big money, and so there's a whole lot of work for hardware and software optimizations and things to make this easier and better and faster. And so eventually we'll see something like that. And there's a huge hype for smaller models because realistically what people want to do is do ML on edge. They want your phone to be able to do everything. They want you to be able to do everything on your phone. And so that 1.8 tera model, that's not going to go on your phone anytime soon. So that's where the smaller models come in. And I think there's an appetite for smaller models, which would be good.
Scans and taking off the data and stuff like that. In terms of AWS and so on, how do you handle privacy of these, or if you're handling medical data or financial data, companies don't want to have a public and the AWS stack that you show me, AWS, using people's data,
So AWS says they're not going to use your data, but they also have AWS artifacts where they go in and they specify service by service what compliance it is. And so if you're building a system that's highly compliant, you have to go in and read the compliance criteria for each of your services. Realistically, I worked at McGill University in genomics data, and actually on a computer cluster that's housed here at BTS. And the best thing for a long time was to keep the data internally on an on-premise cluster, and that was the best way to protect it. Today, that we see less of that. I'm even seeing genomics experts moving to the cloud, and I think the cloud is getting a better reputation, but also the demands, the infrastructure demands are really big, that it's just easier to.
you're running Gen AI models. And
Yeah,
the cost
yeah.
becomes limited.
Yeah.
And the cost is already very high. Having to run it, tokens and stuff like that, like token.
Yeah.
Hosted, self-hosted.
Yeah. And so all of these models tend to be API based, right? They're hosting them. AWS is hosting them. No, not even AWS. Anthropic is hosting their own. OpenAI is hosting their own, and you run API calls for them, and you pay per API call, right? You can host them. You can.
I have a question. You
Yes.
can also run smaller models on cloud infrastructure, like Cloudflare has
Yeah.
Llama 3 or
Yeah. Yeah, you can run the smaller ones on your computer. There's the ChatGPT mini.
I mean, it
Yeah,
runs,
but they come now. They're integrated, the GPU. If no.
I mean, it works, yeah.
Yeah.
It's more of a brain question than an
Yes.
ML question.
My favorite.
So you talked earlier, it was a previous slide we compared models for brains.
Mm-hmm.
I thought what was quite interesting was obviously ML models generally fixed, but I wondered how adaptable the brain was.
So the brain has a the brain is pretty dynamic throughout our lives, and there's something called what do they call it? So I can't remember the scientific term for it, but it's very elastic. And so for kids, and I think the age last I saw was 7 or 8. The brain before 7 or 8 is absolutely amazing. It's forming itself, and so that's why a kid can learn any language before that age, and they learn it really, really well. And part of that is the brain's elasticity, is how fast connections are happening and not happening. And if you have kids or watched kids, it's pretty impressive how it happens. The kid doesn't know how to do something, and then one day they just do, and you're like, okay, like it's like, there was a neuronal connection that just happened, and you're like, okay, that's interesting. So the brain is pretty good. That it's pretty elastic until 7 or 8, and then that closes a little bit with certain channels becoming less active. But we do know that the brain is dynamic, and that we can learn at any age, to a lesser extent. But the brain is pretty good in re-architecting itself to fit with what our needs are.
What makes me think is, could we ever replicate that in ML?
I mean, listen, never say never. Eventually we will, but it's not in the near future. I saw a meme this morning or yesterday who says, okay, Elon Musk said in 2006 that cars will be obsolete because cars will be self-driving, and Jeffrey Hinton was saying radiologists will be obsolete in 5 years. And this was like 10 years ago, and now it's like there's a picture of radiologists in their normal cars driving to their normal work. You know, we are making advances. It's pretty impressive what these things can do. I mean, we work with them all the time, and my own team is impressed with the things that we can do. But the things that are thrown out there from certain business people about how fast this is going to happen is usually unrealistic. Okay. Last one.
Last one.
Okay, I wanted to ask, in machine learning, it's often mentioned that the inner workings of some algorithms are not fully understood.
Yeah.
If that is the case, how does that affect the reliability of their output?
So there's something called black models or black box models in ML. So machine learning models can go anywhere from a small model like AX plus B, which is a linear model. It's very well understood, something to a neural network that has millions and millions of, and when they say it's not understood, it means that we cannot understand what the system is doing. Doesn't mean that it doesn't understand. Of course, it understands what it's doing. We cannot, it's not transparent to us what is happening because of the dimensionality of the data. Now, the reliability of it, of course, depends on really well evaluating the output, right? You have to really understand that. So there was these models. People thought that machine learning systems know what they need to do until a few years ago when they gave it a lot of pictures of cows, and it was like, okay, cow, was great, right? And then they put a cow in the water, and they're like, what it is, and it was like, I couldn't tell because it's not looking at the cow, it's looking at the meadows, and it's part of that context. So we can't tell what the models know. The best way to know if they know what they're doing or if they know what really encodes something is to really test them out a lot. And they can have certain biases and all of that, but that's a really active area in research is how do we, but machine learning models in general don't have a good model of the world. They don't understand the world the way we do. They're just encoding patterns.
Thank you very much.
Good? Thank you.